Method of undetermined coefficients, and this is a method used to solve non-homogeneous ordinary differential equations. We have an example here, which is a second order ordinary differential equation, which is non-homogeneous, y double prime plus 3y prime plus 2y is equals to x squared. So that's what we want to solve using the method of undetermined coefficients. So the first thing is what we call the auxiliary equation. And in the auxiliary equation, we have an equation of the form this. So first of all, we solve the first part, which we take to be the homogeneous part. And we get that the values of R is -1 and 2. And based on the auxiliary part, so what we have is what we call the complementary equation, or the solution to the complementary equation. And so I'll call it YC, y1 e raised to power minus x plus c2 e raised to power minus 2x. So based on that, and we can call this our gx, which is x squared. And that tells us it's a polynomial of degree 2. So that's what we have. And we want to get the particular solution. And therefore, yp, I'm calling it the particular solution, will be equals to ax squared plus bx plus c. Why have I done this? Because I've seen that x squared is a polynomial. So I've created up a polynomial of degree 2. I'm going to differentiate it the first time. And the second time, because I'm dealing with a second order ordinary differential equation. And then I'm also going to differentiate it the second time, is equals to 2a. Now, what do I do with this? I go back to my equation that I had. Remember, I had an equation of the form y double prime plus 3y prime plus 2y is equals to x squared. Since we have this equation, then now we can do the substitution that we have. And we know that y double prime is 2a plus 3y prime, that is 6ax plus 3b, then plus 2 times y, this is 2ax squared, plus 2bx plus 2c, this will be equals to x squared plus 0x plus 0. Why have I introduced 0x? Because this equation is made up of components with both x and x squared. So the first part of the equation is 2a x squared is equals to x squared. And so if I divide through by x squared, I'll be left with 2a is equals to 1, and that tells me that a is equals to 1 over 2. So the first component that I dealt with was this. The second component will be this. And then the third component will be this. So I'll go to the second part, which is 6a plus 2b times x is equals to 0x. So basically, if you divide through by x, I'll be left with 6a plus 2b is equals to 0. And 2b is equals to negative 6a, which equals to negative 3. And therefore, b is equals to negative 3 over 2. So that's the value of b. And therefore, we're now able to get the value of c. And the value of c is given by 2a plus 2b plus 3b plus 2c is equals to 0. 2c is equals minus 2a minus 3b, which is equals minus 2 times a half minus 3 times negative 3 over 2. So this is given by minus 1 plus 9 over 2. LCM is 2. Minus 2 plus 9 is equals to 7 over 2. And therefore, I'm able to get the value of C. C is equals to 7 over 4. Remember, the particular solution was given by ax squared plus bx plus c, because we are dealing with a polynomial of the second degree. And therefore, I could say y particular will be given by a half x squared minus 3 over 2x plus 7 over 4. And now we can get the general solution. And the general solution is given by the particular solution. The general solution is given by particular solution plus the complementary solution. C1 e minus x plus C2 e raised to minus x 2x plus a half x squared minus 3 over 2x plus 7 over 4. And those you've been told to solve y double prime plus 9y is equals e raised to power 2x. The first step is you get what we call the auxiliary equation. So the auxiliary equation is given by r squared plus 9 is equals to 0. And if we solve that quadratic equation, it will give us r is equals to 3i plus or minus 3i. Now, based on that, then we can get what we call the complementary equation. And the complementary equation is given by, I call it yc, c for complementary, is equals to cos 1 cos 3x plus c2 sine of 3x. So we have solved the first part, which is the homogeneous part. So if it was an homogeneous equation, y double prime plus 9y is equals to 0, then this would have been the solution. Now, but because it's non-homogeneous, we go to the next step and we get what we call the particular solution. And the particular solution will help us to solve the non-homogeneous part of that problem. And therefore, I'll call it yp, which depends on x. I'll give it a constant a, which is unknown, and then I'll write the non-homogeneous part. And then because I have y double prime, remember my equation is y double prime plus 9y is equals to e raised power 2x. I'll need to get the second derivative of yp. It's 2a e raised power 2x. And then I'll get the second derivative of y, which will give me 4a e raised power 2x. Now, going back to my original equation, I can comfortably say 4a e raised power 2x plus a e raised power 2x is equals to e raised power 2x. So I'm using this equation, but now I'm substituting with a particular solution. So if I divide through by e raised power 2x, then I have, remember this is 9 times y, and y is a e raised power 2x. So it will be 4a plus 9a is equals to 1. And therefore a is equals to 1 over 13. I can comfortably say my particular solution is 1 over 13 e raised power 2x. Because my yp was a. And with that, then I'm in a position to conclude because I've gotten my particular solution. And my general solution for this non-homogeneous equation, which I'll call it y, it is yc plus yp. And that gives me c1 cos 3x plus c2 sin 3x plus e raised to power 2x divided by 13. And that gives us the solution to our non-homogeneous ODE using the method of undetermined coefficients.